Hello, this is lesson 2.3 on symmetric matrices. Just two definitions, but they have a lot of importance and many applications, as we'll see. So the first definition is the definition of the transpose operation. If you have an n by m or m by n matrix, so m rows, n columns, so the transpose of A, which is denoted A subscript T, is obtained by just swapping the rows and the columns of A. Okay, so that is going to change a few things. It changes the size, so the size of A transpose is not m by n, but n by m, since the rows become columns and vice versa. And the elements are all going to be different also. So the element ij of A, it becomes the element ji of A transpose. So just for example, if you have the matrix 0, 1, 5, 2, 6, 8, this is a 2 by 3 matrix. If you transpose it by putting the little t on top like this, this becomes now a 3 by 2 matrix. The first row of A becomes the first column of AT, so 0, 1, 5, and the second row, 2, 6, 8, now is the second column, like this. If you have a square matrix, the transpose changes the position of the elements but does not change the size of it. Another interesting example is if you have two vectors. Let's say you have the vector 1, 2, 3, and if you transpose it and multiply the vector 4, negative 1, 2, so these two vectors, if you did not have the transpose, could not be multiplied. But now that we have the transpose, the first column vector becomes a row vector, 1, 2, 3. And the second stays the vector 4, negative 1, 2. Now these two can be multiplied because this is a 1 by 3 size matrix. And this is a 3 by 1. And so this is 4 times 1 minus 2 plus 6, which is equal to 8, a scalar. And notice this is equal to just the dot product between these two vectors. So therefore we see that another way of writing the dot product, if you have a vector A dot a vector B, is to write the vector A transpose times the vector B, using matrix multiplication instead of the dot product. So we will use this several times in the future. Okay, so whenever we define a new operation, we have to define all the properties of this new operation. So first of all, if you have the sum of two matrices, A plus B, and you transpose the sum, you can distribute the transpose, A transpose plus B transpose. Scalar multiplication is the same. The scalar can be floated outside of the transpose. Another interesting one is if you have a matrix A and you transpose it, and then you transpose it again, you recover the original matrix A, which should be very obvious. The next one is not so obvious. A times B transpose is equal to B transpose times A transpose. So matrix multiplication becomes reversed when you distribute the transpose. This is the only one that I'll prove because this one here is the only one that is not obvious. So let's start with looking what happens element by element. So if you take AB and IJ, let's call this the IJ element of the matrix AB. Okay, similarly, we're going to take the matrix B transpose A transpose and look at its element IJ. So the way you calculate the elements of a product of two matrices is you take the ith row of the first matrix and you do the linear combination with the jth column of the second matrix. So this you can kind of symbolize a little bit informally as row I of BT, linear combination with column J of AT. And so here this is the, you can call this linear combination. So you take the corresponding elements in the row of I and the column J of AT, and you go all the way through the row and through the column doing linear combinations, and the result is the element IJ of BTAT. Anyway, row I of BT, because it's a transpose, is the equivalent of column I of B, which you combine with row J of A. So these linear combinations are commutative, so you can just write this as row J of A times the column I of B, and this is by definition then the element Ji of the matrix AB. So, which is by definition of the transpose, the element IJ of the transpose of this matrix. So it's AB transpose element IJ. Okay, so we see that element IJ of AB transpose is the same as element IJ of BTAT. So that proves this theorem right here. And by extension, you can do this with a longer product. So for example, if you have A times B times C times D, etc., a long product that you transpose, the transpose reverses the order. D transpose times C transpose times B transpose times A transpose, etc. So the second definition for today is a symmetric matrix. which is a matrix that is equal to its transpose. So that implies that it has to be square. So a square matrix A is symmetric. If AT equals A. So here's an example of a symmetric matrix. So let's say 1, 6, 3, 8, negative 2, 0. And then the other elements are given by this. So you see we have this main diagonal, which acts as a mirror or as an axis of symmetry with this matrix. These numbers that are on either side have to be the same for the matrix to be symmetric. You see this matrix, if you swap the rows with the columns, you don't change the matrix. Okay, before we look at some applications, let's look at another definition for a square matrix. So the trace of A, which is denoted TRA, is the sum of the elements in the main diagonal. So mathematically you can write this as TRA is the sum of all the elements of the form AII. These are the elements on the main diagonal from 1 to n. So for example, if we take this matrix right here, 1, 6, 4, 6, 9, 9, 3, negative 7, negative 3. Then the trace of this matrix is just the sum of these three numbers right here. 1 plus 9 minus 3, which is equal to 7. So this trace is useful in many theorems, as we'll see a little bit later on. So the properties of this operation are, most of them are very straightforward. The trace of a sum is equal to the trace of A plus the trace of B. Same thing with the scalar multiple. The trace of C times A is equal to C times the trace of A. So the trace of AB is equal to the trace of BA. And the trace of A transpose is equal to the trace of A. Because when you transpose a square matrix, the diagonal elements do not change. Okay, so there are many, many applications that make use of this concept of transpose and symmetric matrices. I'll just mention a couple of them here. So there's a deep relationship between linear algebra and graph theory. A very large area of application in mathematics. Let me just define what a graph is within the context of graph theory. So a graph is just a set of vertices that are connected by edges. It's very general. You can use it for a lot of different things. So a graph is a set of vertices together with a set of edges and these edges connect some or all of the vertices. So here's an example of a graph. This graph has 4 vertices that I'm going to label 1, 2, 3, and 4. And I'm going to put 4 edges, one right here, one right here, one right here, and one right here. So this means that 1 and 2 are connected by this edge, 1 and 3 are connected, 2 and 3 are connected, 1 and 4 are connected. 2 and 4 and 3 or 4 are not connected because there's no edges. So 4 vertices, 4 edges, this is all that a graph means. Anyway, so linear algebra comes in because you can describe these graphs using matrices in different ways. So here's one way. So this definition is for the adjacency matrix of a graph. So this indicates which vertices are connected. So connected meaning they have an edge between them. So here's an example. If we look at this little graph that we had above right here, you can define the matrix A, and because there are 4 vertices, this is going to be a 4 by 4 matrix. Each row and column represents a vertex. And then you just put 1s or 0s in the elements. 1 if the 2 vertices are connected, and 0 if they're not. So we're going to assume that the vertices are not connected to themselves. So you have 0 on the main diagonal. 1 is connected to 2, and 3, and 4. That means that 2 is connected to 1, 3 is connected to 1, and 4 is connected to 1 as well. 2 is connected to 1 and 3, but not 4. And 3 is only connected to 1 and 2, but not 4. So this is what the adjacency matrix looks like. So notice that this is matrix A is only filled with 1s and 0s. Those are the only values that the elements of an adjacency matrix will have. Furthermore, A is square, and it's also symmetric. Because again, we assume that if one vertex is connected to the other, that other is connected to the first one as well. So, in the exercises, we'll see some applications of this. You can take this even a step further and define a weighted adjacency matrix. Which is very similar, except that you assign a weight to each one of the edges. And so the only difference in this matrix is that the elements are no longer just 0 and 1s, but they can take on any other value. So for example, if we have a graph, let's just assume we have 4 vertices again, 1, 2, 3, 4, and let's assume we have the same edges as above. But now they're not equal edges, so let's put a weight of 1 right here, 2, 3, and 5. So now we can call this matrix D. It's also going to be a 4 by 4 matrix, and it's also going to be symmetric. So again, we're going to assume 0 on the main diagonal. But now 1 is connected to 2 using an edge that has a weight of 2. So we put a 2 right here. Similarly, 1 and 3 are connected with an edge of 1 and 5. This is symmetric, so these 2, 1, 5 reappear here. 2 and 3 are connected with an edge of weight 3, so this 3 appears here. And 4 is not connected to 2 or 3, so in these two spots we're going to put X's to indicate that it's not that we have a edge of weight 0, it's the fact that there is no edge at all. So this matrix D is also square and symmetric. One application of D would be a distance matrix, for example. If these are points on a map, you could indicate what is the distance between two different points using this kind of distance matrix. So another application, which is a little bit more exotic, but it's described in your book. It has to do with sequence dating in archaeology. So archaeologists go out and they dig out pottery out of graves, and their goal then is to be able to date the graves and to create a sequence, a chronological sequence of their digging sites. So if we assume that we have M graves and N different types of pottery, and the archaeologists are able to find different kinds of pottery in the different graves, they can come up with a table that looks like this. It's a table that has the different grave sites on the left here, grave 1, grave 2, all the way to grave M. And the columns indicate the types of pottery. So you can have pottery 1, pottery type 2, etc., all the way to pottery type N. And they can indicate in this table then if the certain type of pottery was found in the particular grave either by yes or no, so you can fill in these blanks by either yes, no, yes, no, etc. And you can fill up the whole table this way. Okay, so this table very naturally gives rise to a matrix, you see. So it's a matrix that recapitulates the information of the table. You put a 1 if the answer is yes, and a 0 if the answer is no. So here you would have 1, 0, here you would have 0, 0, 1, and then at the bottom 1, 0, 0. Okay, so this matrix A is generally speaking not a square matrix, but it has size M by N. M graves and N types of pottery. You can call this the archaeology matrix, for A for archaeology. So the goal, like I said, is to be able to date the graves into a chronological sequence. So there's a few different additional matrices that are used to do that. So first of all, let's look at the grave matrix. Capital G. And the grave matrix G is defined as being A times A transpose. So the size of this matrix, A is, as we said, m by n, and it's multiplying its transpose, which has size n by m. So the multiplication is possible, and you see that the final size is m by m. So this matrix is square, and it also happens to be symmetric, as can be verified. So if we look at the elements of this grave matrix, so the elements G, Ij, which we can use the same kind of informal concept that we used a minute ago, is obtained by taking linear combinations of row I of matrix A with the column I, or column J, of A transpose. Okay, and this here again is a linear combination. So we can change the column J of A transpose by row J of A, so it's row I of A with row J of A. So what we're doing is comparing two rows in this archaeology table right here. If you compare two rows and assume that there's only 1 and zeros, then all the terms of this linear combination will either be 1 or 0, and they will only be 1 if both graves have the pottery of that type in it. This means that this Gij is the number of pottery types that are common to the two graves in the two rows I and J. Okay, and this is where you get the information that you need, because then the archaeologists assume that the greater the number of pottery types common in the two graves, the closer they are in time. So the greater number is equivalent to the graves closer in time. So you can use that to cluster the graves in terms of common eras and look at which one of them occurs in what sequence versus the others. Okay, so that's the grave matrix. There's another matrix that can be built off of the same matrix A right here, so I'm going to just use this continuation. And let's call this the pottery matrix. Capital P, which is defined as a matrix A transpose times A. So the size of this matrix, A transpose, is now n by m. And it's multiplying A, m by n, so the multiplication is possible. And the final size is n by n. So once again, this matrix is square and symmetric. But the number of rows and columns now is the number of types of pottery. So if we look at the elements of this matrix, just like we did before, if we take an element Pij, it's obtained by taking a linear combination of the elements of row I of At with the elements of column J of A. And row I of At is column I of A, so you can write this as column I of A combined with column J of A. So you see what we're doing now is comparing two different columns in the same matrix, right, in the matrix A. Again, these elements can either be 0 or 1, depending on whether you are multiplying 1, 0, or 0, 0, or 1, 1. And will only be 1 if you have 1 in both columns in the same grave. So this means that this is the number of graves that contain both types of pottery, I and J. Another piece of useful information that's used in archaeology. So these are simple operations on matrices that are derived from tables of data. And we'll see in the exercises other applications of symmetric matrices and combinations of matrices of this type.